Good afternoon, everyone, and welcome to today's webinar titled Correlating Oil Analysis Data. My name is Taylor Colon, and I am your Customer Engagement Specialist at Test Oil. I'll be your host today. Before we get started, there are a few things I wanted to go over. First, everyone is muted. We are recording today's presentation, and by being on mute, this will ensure a high-quality recording. Second, please feel free to use the questions box in the GoToWebinar application. We would be happy to answer any questions that you have. Finally, the webinar recording will be distributed later today along with a survey. Look for that in the email that you registered with. Let's get started. Today's webinar is presented by Evan Zabowski. He is OMA1, MLT1, MLA2, and CET certified. Evan is also certified as a certificated lubrication specialist with diplomas in chemical engineering. Evan has been a member of STLE for over 18 years and also serves as a senior tech advisor at Test Oil. All right, Evan, if you're ready, I will pass the controls over.
Great, thank you, Taylor. So today's presentation is on correlating oil analysis data with the ultimate goal of trying to explain why some results will correlate with each other and why sometimes they don't. But when they don't, what can we still glean as useful information from that apparent lack of correlation? So I chose to break this presentation into two sections, one based on routine analysis, the kind of data most folks get on most reports, and another section I called advanced oil analysis data, which primarily focuses on degradation type testing, so MPC, ruler, ultracentrifuge, RPVOT. Now, the simplest way I try and phrase the entire presentation is if two results were supposed to correlate exactly with each other, there would be no point of running both tests. What I mean by that is if two different tests ultimately told you the same thing and the results would move in either similar directions or at least in direct relationship with each other, there's no point in running the second test to confirm what one test already tells you. So by and large, most of the testing that has been selected for routine testing is meant to present you with a slightly different viewpoint of maybe perhaps similar data, but still it will not be exactly the same measurement that's being performed. So to begin with, I chose one of the more common correlations that people try and make, and that is between elemental spectroscopy and particle counting. So to quickly explain elemental spectroscopy and what we need to know to understand the correlations do or do not exist is to understand how the test is performed. So elemental spectroscopy is performed by diluting the sample and turning it into an aerosol and injecting it into a plasma. So right away you should understand that the sample is going to be quite thin. It has to be aerosol, so it's going to be fine droplets, and it's placed in a plasma. Now, when it's in this plasma, we ionize the sample. For lack of a better word, it's kind of like burning it. What happens is it gives off light. When it gives off light, we measure the intensity of that light at certain key wavelengths, and we know exactly what is in the sample. But here's the fundamental aspect of that. We only know the elements that are in the sample, not the compounds, not the alloys, not the chemicals. So when we have something like, say, Babbitt ware, we won't see Babbitt show up on the report, we will see lead and tin show up on the report. However, if we have brass or bronze ware, both of those contain lead and tin, the differentiator being they will also contain copper. So when we see something like lead and tin on a report, we always look for the correlation to what other metals might be present. Like I said, if copper happens to also be there, we can now enter into consideration like brass or bronze. Now, the correlation between each of the elements can help confirm to us if it is an alloy, in which case all those ware elements would be proportional, or if it is perhaps a coating or a layer, in which case these elements will not be proportional to each other. But for the sake of our discussion with particle counting, we need to understand that, one, this is an elemental concentration. So it is telling us what makes up the particles, not necessarily what each and every individual particle is comprised of. Now, the second fundamental thing about this test is it is really only accurately measuring particles in the 0 to 5 micron range. In that range, these particles will be part of the aerosol that is injected into the plasma and will be read accurately. After about 5 microns, the accuracy begins to drop off, and somewhere in the 8 to 12 micron range, the accuracy takes a significant nosedive and is no longer considered to be that accurate. So you may have heard this said before, and some people will say that the instrument is blind to particles greater than 10 microns or some number thereabouts. It's not really blind, it just doesn't measure them accurately. So the values are, a bit suspect. Now, particle size range is very important in understanding why results do or do not correlate. So with this test, we just need to appreciate it is the 0 to 5 micron range, and this is, of course, the smallest of the small particles. Now, when you first hear this number, you might be concerned that, well, wait a minute. Elemental spectroscopy is supposed to measure wear, additives, and contaminants. How many of these things fall in that range? Well, wear particles generated under normal wear modes should be in the 0 to 5 micron range. Additives are submicron, so they'll definitely be within this range. And contaminants that are of the normal type, meaning airborne particulate, and that is also in that 0 to 5 micron range. What isn't in this range are wear particles from abnormal wear modes and severe contamination. So first and foremost, before we even compare this to particle counting, we should appreciate that if it's gone to an abnormal wear mode and or due to severe contamination, this test probably won't give us any of that data. It is not meant to measure within that range. It simply does not have that capability. So that is the very fundamental aspect that we have to appreciate. Elements only and very small particles, 0 to 5 microns. Now, I've also listed some interferences just so we understand why sometimes the numbers get a little bit screwy. But as I said, we do dilute the sample to turn it into an aerosol. If it doesn't dilute, well, it doesn't get measured very well. So we will have to alter the solvent accordingly. As well, water content can skew the result. It's not that it interferes with the dissolving of the sample or the aerosol, but what it does is when the water enters the plasma kind of sputters. So it affects the stability taking a reading from the plasma. So when we have a high water content sample, we sometimes take a hit on accuracy here. But as I always point out, if I've got that much water in my sample, it's skewing this particular test, that's my problem. I don't need to worry about the wear elements or the contaminants because whatever's happening may be in part due to the high water content. So leaving that test for a second, let's go to particle count and understand the fundamentals of particle counting. Now, particle counting can be done one of two methods. And I'd just like to point out how each method works because not a lot of people understand exactly what's being measured. So in your standard optical particle count, and this is the format that would be used in most portable particle counting equipment. So if you have an on-site tester or anything like that, or an inline sensor, this is the technology. We call it an optical particle count because it is using visual light. So it is a bright light source being shone through a thin film of sample. It is flowing sample, so it's moving sample. And that light is focused at a photoreceptor, an image sensor, not a lot different than what you would see in a digital camera. Now, as the oil flows past the light source will project onto the sensor. The sensor will detect shadows. So what's being counted is actually shadows. Now, how the shadows are sized is what throws most people off. The shadow is measured for its area, not its longest dimension, not its smallest dimension, and not its average dimension, but its area. And the area of the shadow is then calculated to what we call spherical equivalency, meaning the particle is assumed, and this is a big assumption, it is assumed to be a perfect sphere, a ball, if you will. So the question is, the area of that shadow, what size circle, because a sphere would be a circular shadow, what size circle, what is the diameter of that circle that would create the same area of shadow? What I mean by this is, as an example, say a 10 micron long but 1 micron wide particle went past the sensor. Well, depending on how it oriented itself as it went through the flow cell, the shadow that it would cast would be, say, roughly 10 square microns. Well, when we do a spherical equivalency on that, and based on the roughness of the particle and whatnot, we might measure out that particle to be 3 microns, because we would say it's a 3 micron diameter circle would equal the same area. So that's what we need to appreciate, is optical particle counting does not measure the true size of the particle. It is not the longest, nor the shortest, nor the average dimension. It is a spherical equivalency. A perfect circle is assumed to be the size and shape of the particle. Now, the other limitation to this test is, of course, it doesn't tell us what the particle is. It's just a count. So how many of what size shadows went by? The other to note, and this is where it comes to play back with spectrometric analysis, is this test is measuring essentially 4 microns and up. Now, the upper range of this test is determined by the instrument. Essentially, around 100 to 200 microns and larger particles are not counted, simply because the flow cell is about a 100 micron gap. So if the particles are significantly larger than that, they simply do not enter the path. Now, with optical particle counting, because it is counting shadows, it should be noted as an interference. Anything that creates a shadow will also be counted. So I've listed off here soft particles, meaning any of the insolubles, the stuff that eventually becomes varnish, as an example. Air bubbles and water molecules can all be counted. So generally speaking, in a laboratory environment, we will dilute and sonicate or vacuum your samples to remove these effects. However, on-site or inline particle counting doesn't do this. So that's why most on-site or inline particle counting tend to skew higher than laboratory results. Now, the other method we have for measuring particle count is what we call pore block. Now, some of you may have heard this as referred to as flow decay. They're one and the same. The basic principle of this test is we take a screen, which you see pictured off to the right there, and it is calibrated so that all the pores are in the same rough dimension. And what we do is we push the sample through the screen at a constant pressure. What we measure is how fast the flow decays. By taking the flow decay, we're now extrapolating this against our calibration, where we assume, and again, here's where the assumption comes into this test, a linear distribution of particles. So what we're assuming is that the particles that will first begin to plug the pores will obviously be at the pore size or larger, but then what will start to happen is the particles that will begin to be trapped will be smaller and smaller and smaller, because there'll be fewer and fewer holes to go through. So there is an assumption built into this test as well. But the nice thing about this test is, though it's not measuring, again, necessarily the longest, the shortest, or the average dimension, it's just will it plug up in the hole, it doesn't have any interferences. Soft particles, water, and air bubbles go right through the screen, and they don't cause us any issue. So this form of particle counting tends to correlate better with on-site testing as it would with laboratory-based testing. Now, the limitation to this test, as you can see, is based on screen size. So screens can be different micron ratings. Typically, we choose something like a 10 micron screen, and then we're in the middle of the particle count range that's usually reported out. So understanding that elemental spectroscopy is 0 to 5 microns, however, particle counting is essentially around 4 microns and larger, you should quickly be able to see that we're not exactly measuring the same range of particles, even if they are in fact the same particles. Unless they're roughly around 4 to 5 microns in size, it's quite possible that only one test will essentially see or measure those particles. So when it comes to comparing these two tests, we need to understand, is there a correlation or is there not a correlation? Now, when a correlation exists, we know that we've got particles in both ranges. So we've got both small and large particles. When no correlation exists, well, that means we've got all the particles mostly in just one of those two ranges. So the way to interpret the results is, if both your results are low, this is going to suggest that, of course, there's very little wear and or contamination present in the sample. If both are high, though, this is going to suggest that we have small particles from normal wear modes and normal contamination. That's what spectroscopy is telling us. But we also have some large ones from perhaps abnormal wear modes or severe contamination. So it's suggesting we're probably transitioning from the more normal things to the more abnormal or severe. If we just have high spectroscopy but low particle count, then we're dealing with mostly normal wear mechanisms, normal contamination. If it's the opposite though, and the spectroscopy is low but the particle count is quite high, then the suggestion is that we must have very large particulate present, and therefore it's either severe contamination or severe wear particles being generated. So that's sort of how the teeter-totter goes back and forth, right? Both lows probably okay, both high indicates the transition period. One high versus the other one being low can indicate either extreme. Now, sticking with the thoughts that we have here on spectroscopy, let's just throw in one more test. Ferrous wear concentration. Now, ferrous wear concentration is a screening type test that is performed to obviously measure ferromagnetic material. Now, the way this is measured is we take a syringe of sample and we introduce it into essentially a magnetic flux coil and measure the change to the flux. So as long as it's ferromagnetic, which is going to be anything that is obviously iron, but also there are other elements like cobalt and chromium that can be measured, it will change the flux in the coil, indicating that there are magnetic particles present. Now, given we're inserting a large volume of sample into the flux, the key thing to take away from this test, there's no limitation on particle size. It doesn't matter if it's a bunch of smalls or one large, it will, in effect, measure out to a similar value. But the key thing here is because it's measuring any size particle, not just 0 to 5, it will not correlate necessarily with the elemental spectroscopy. Now, as for interferences, I already listed off that it's more than iron that can be measured, although cobalt is a fairly rare element to find in oil analysis, but chromium is a common element used in many coatings and certain alloys. So we will sometimes see a slight skewing of results just based on that. But when we take a look at the correlations now between these two tests, we're covering pretty much the same ground. We have to appreciate that spectroscopy is a limited range of particles, whereas ferrous wear is not. So if we see a correlation between the two results, we've got a wide range of particle sizes. If the correlation does not exist, they're only in one or two ranges. So this is very similar to what we just said about particle count. So the simple way of looking at it is if both results are low, there's probably not a lot of wear happening. If both results are high, again, this would be one of those transition periods where we're moving from normal wear modes to probably abnormal or severe wear modes. If spectroscopy is high, but the ferrous wear is low, then this is suggesting most of the particulate is going to be from normal wear modes and maybe of lesser concern. But if it's the other way around, the spectroscopy is low, but ferrous wear is high, then most of the wear we're seeing is from abnormal wear modes, and that would be considered to be a much more severe problem. And so as you can see, whether we look at spectroscopy and compare it to particle count or compare it to ferrous wear, the same logic applies. It's basically the same sort of philosophy in terms of what that teeter-totter looks like if both are low compared to if both are high, and if only one side of it is high. So moving on to some different testing then, let's talk about viscosity for a second. Now, viscosity is a pretty simple measurement. It is done in a glass capillary tube. We allow it to flow under gravity and gravity alone at a set temperature. So the longer it takes to flow down the tube, the thicker the oil measures out to be. Now, the key limitation to this test then is that capillary. It's a very fine bore. It's about the size of mechanical pencil lead. So any sample with significantly large particulate in it might actually plug the tube and you wouldn't get a measurement. As for interferences though, because we are heating the sample and expecting it to flow, if there's anything volatile in the sample, so fuel, solvents, refrigerants, those kinds of things, might boil in the tube. So while we're trying to measure the flow going down, we will have bubbles going up. And if those bubbles are going up, it really messes up the measurement. So where we tend to see this is in samples with particularly high water content, or very commonly in screw compressors, only because screw compressors tend to push whatever medium it is they're compressing into the lubricant, and the samples become quite gas-filled. Now again, as I said, if I have a sample that's got such high water content, it starts affecting one of my tests, that's my problem. So I don't really concern myself with the fact my viscosity might not be an accurate measurement when I have a lot of water content, because I know what's driving that water content. But there's more to it than that. So before I get to water content, let me talk about acid number. Now, acid number, just so we're aware, like particle counting, can be measured in two different methods. Now, both methods are very similar in the regard that they use the same solvents, they use the same titrants, it's all the same concentrations, and it's all the same volumes. The difference between the two methods is how do you know when the test is over? So the first way that we like to do particle counting is by ASTM D974. Now, D974 is known as the colorimetric method, and it is counting on a color change occurring. So the color change, as you see in the picture, is when the sample turns from a bright orange to a dark greenish brown color. That's how we know if we've neutralized all the acids in the sample. So the idea behind this test is we measure how much base it takes to neutralize the acids, and by measuring how much base it takes and the concentration of the base is known, we know how much acids are present. So the limitation to this test is that it is going to measure acidic constituents in the test, and these build up typically rather slowly, and they're a measurement of a concentration. So the larger the volume that the reservoir or sump is, the slower this particular test is to react to degradation. So by saying that, what I mean is in large reservoir applications, we tend to rely on other testing to indicate severe degradation is occurring. Now, the interferences with this test is that since we're looking for a color change, if the oil is already a dark color, it sometimes is harder to see the color change. So we might have to dilute the sample a little bit further, and we might suffer a little bit on the accuracy. But the other effect, again, here comes water content. High water content in this particular test means that while we're testing it, acids that might actually form and test. So essentially, we're kind of chasing the answer, and the results tend to skew a little bit high. But like I said about the other tests, if I've got high enough water content to cause this to be my problem, again, I know what the problem is in the lubricant. It's water content. Now, the other variation of this test is called D664, and it is known as the potentiometric titration. The only difference between this test and the other one is instead of knowing that the test is over by a color change using an indicator, we just measure essentially its conductivity. So by measuring a potential in the fluid, we can determine when the inflection point occurs, and that is when the sample has been fully neutralized. So it's all the same type of testing, except for the analysis of when the test is over. So the limitations still hold up. The interference regarding water content still holds up. It just doesn't the interference based on color. So one quick comment between these two tests, and this is very important for people who look up product data sheets, is right from ASTM, they will tell you that the acid number obtained by one method might not correlate with the acid number obtained by the other method. So what this means is if you're looking up baseline values and you're just going based off of a product data sheet, look at the test method for that baseline and ensure you're comparing apples to apples. Obviously, if you send a sample into the lab and get the lab to do the baseline, they will use the same method every time. But there have been people caught off guard by what product data sheets have to say for themselves compared to what the in-service samples have to say. So it's just a quick little side note here. But returning to our two tests that we're talking about, viscosity and acid number, if the correlation exists, well, then probably something related to degradation is occurring, either no degradation or a lot of degradation. If the correlation doesn't exist, though, that's when we can key into something else is happening. So again, looking at our kind of teeter-totter here, if both are low, probably not much degradation is occurring at the moment. Now, if both are high, then this would suggest significant degradation is occurring because as the acids form in the oil, it will drive the viscosity up slowly. So this doesn't cause very significant changes in viscosity, but rather fairly linear changes, and that the longer it's in service, the thicker the oil will become, and it might thicken to the point that it falls outside of the specification or grade that the oil is meant to be in. Now, when the correlation doesn't exist, if we have a high viscosity, but the acid number doesn't seem to be the contributing factor, then what we're suspecting then is that we've probably mixed with a thicker lubricant. That's probably the most common cause for a high viscosity without a change or significant change in acid number. If it's the other way around, but the viscosity is low, yet the acid number is high, then either we've also mixed in a thinner lubricant, I mean the acid number still clearly indicates degradation has occurred, or if we're dealing with high viscosity index products or multi-grades, it's possible that the oil is shearing more than it's thickening, and we will see a net result of a decrease in viscosity. So like I said, we don't always see these changes, and one of the key factors is large volume applications. The larger the volume, the less change you will likely see in both of these tests due to degradation. When we have under a couple hundred gallons, we probably will notice increases in viscosity and acid number, but when we start having systems that are 1,000 gallons, the amount of degradation that is required to alter the viscosity or acid number significantly is actually quite severe. So typically we'd see other results changing much more rapidly than these two particular tests. Now, sticking with viscosity for a second, let's talk about a different test to compare. What about water content? Well, again, water can be measured one of two ways, so we need to appreciate at least what the difference is. Now, the common way that almost all samples are screened at any lab would be by crackle test. Now, the crackle test is an incredibly simple test. We just take a few drops of oil, place them on a hot plate, we look for bubbling, we listen for crackling. If we get both, we suspect that's water. Now, the sticky point here is the common question related to this test is, well, what is the detection limit? How low is the water content going to be that this test will still yield a positive result? Well, I kind of like to look at it from the opposite perspective. I want to ask myself, how high could the water content be and this test still give me a negative result? Meaning I still might show that the crackle test is indicating no water. So to that end, Test Oil did their own study here. There's nearly 500 samples that we're looking at of various types of fluids. And what you see in the right-hand columns is the lowest positive result that crackled, where the water content was confirmed by the Carl Fisher titration. But you also see what was the highest negative result, and water, again, was confirmed by Carl Fisher titration. So rather than using the left-hand column of lowest positive as my detection limit, I'd much rather direct attention to the highest negative. So that is the highest amount of water content that we got in each one of those types of samples, whereby the crackle still would have shown up as negative. So as much as you may have read literature that suggests that the detection limit for a crackle test is around 250 to 500 ppm, if you look at these results, it's suggesting it's more like 1,000 or higher. So understand that if you've got a very sensitive system to water content, you shouldn't rely on crackle test alone. You should go to Carl Fisher. Now at Test Oil, we do test all positive crackles with Carl Fisher, so we can give you an accurate number. Now, how we do that is what's known as the Carl Fisher titration. So the other method for measuring water is, again, a titration, much like acid number. All we do is we use a hydroreactive chemical and we measure how much of that we need to neutralize all the water sample. It tells us how much water content is there. Now, just some neat trivia for you in terms of problems. Water is the #1 cause for diesel engine oil related failures, and it's the #2 cause in industrial applications. If you're wondering what the #1 cause in industrial applications is, it's particulate. So this is why we focus on the particle counts and water content so much. Now, the limitation to a Carl Fisher test is it doesn't identify what phase the water is in. So it doesn't know if it's dissolved, emulsified, or free. It also doesn't know where the water is sourced from. It can't tell the difference between, as an example, fresh water, seawater, or even process-related water. So we don't get any solid information there. We just know how much water of any type is present. Now, the interferences to this test, just so you know, are anything sulfur-related. Those can skew the test a little bit. So if we have a sour application, understand our water content by Carl Fisher may not be as accurate as we would hope for, but still, if you're trending it, you get an overall feeling if the water content is increasing. Now, comparing these tests, again, we look for the correlation and ask ourselves, well, what is going on here? So similarly to acid number, water content will accelerate degradation. So that's where we're thinking the common factor is. If both viscosity and water content are changing together, we're probably going to experience more degradation. If they're not, then something other than degradation will be occurring. So sticking with my teeter-totter here, if both are low, then we probably just mixed with a thinner product. That's why the viscosity is low. If both are high, this is a severe problem because chances of water content so elevated, we're now forming an emulsion. And an emulsion is when, generally speaking, two products that normally wouldn't mix together formally mixed together, and the end result is an overall increase in viscosity, a thickening. So this is not a good situation to be in. It means that we've got significant water contamination and we've got a change in viscosity, so our lubrication will not be the way it was intended. Now, if we do have a high viscosity with a low water content, well, that's not an emulsion anymore, but it probably suggests that we've added a thicker product in there and driving the viscosity to be higher. Because if the viscosity was high but the water content was low, I wouldn't necessarily assume it's degradation, because chances are what having degradation to be significant enough to increase the viscosity would actually be water-related contamination. If it's the opposite and water content was low, water content was high but the viscosity was low, then we're probably looking at the fact that water being thinner than oil is actually thinning the lubricant, yet we're not forming an emulsion. So it's significant water contamination, but it doesn't have an end result of an effect on viscosity, which means that if we deal with it soon, we can probably mitigate some significant problems. Now, those are the routine tests. So these are the tests that I felt that most people probably saw in most reports and were the correlations that are frequently looked for, but not always seen. So hopefully that has shed some light on, well, if you see the correlation, what is it still telling you? Moving into what I call the advanced oil analysis testing, this is where I'll get into degradation tests. So the first test I'd like to speak to is the RPVOT. Now, the picture does it quite a bit of justice. If you look at what we're seeing here, we take the 5-gram sample of water with a 50-gram sample of oil, we put it in a beaker, and we place 3 meters of copper wire in there. So we've got copper. What we do is we take that glass beaker, we insert it into a stainless steel pressure vessel, and we purge out all the air and replace it with oxygen. So now we've got oxygen, water, and copper. 3 sides of an oxidation triangle that desperately want to react with each other. The only thing preventing them from doing that is the oil itself. So we rotate this at a slow 100 RPM to keep the oil constantly splashing over top of the copper coil, and we measure the reaction based on pressure. So when we first stick this pressure vessel inside the bath, which is at 150 degrees Celsius, the pressure increases rapidly because the oxygen is now being heated and will pressurize. What we do then is, after the pressure is stable, we wait for a certain amount of pressure drop. The pressure drop indicates to us when the oxygen has been consumed, meaning when it has formed copper oxide, which is a result of the oil no longer protecting the copper. So the long and the short of this test is it's a kill test. It is a very rapid kill test. The results occur within minutes, which are typically measured within the hundreds to thousands of minute range. And what we do is essentially trend the results from this particular test. And by comparing the trend to the surface of the oil, we can predict when to change the oil. So this is very much a performance-based test. We're actually putting the oil through some form of trial. We're not just measuring a single property on it. So that is important to understand. It's a performance-based test. We're making it jump through some hoops. Now, the limitation with this test is the only oils we can test have to have an antioxidant or oxidation inhibiting additive chemistry, which means fluids like phosphate esters typically cannot be tested. As for interferences, it doesn't really have any that cause any significant change here. So that's the good part. Now, when it comes to looking at this oxidation test, most people are looking for confirmation that significant degradation is occurring or potentially will occur. So the common tests that we look for, surprisingly, actually don't correlate very well with this test. So remembering that this is a performance-based test, VOT will not necessarily correlate with viscosity, which is a physical property. It will not necessarily correlate with acid number, which is a chemical property, and NPC, which is basically a measurement of a contamination level, doesn't necessarily correlate. And ruler, though is aimed at antioxidant testing, it is a direct measurement of the amount of antioxidant, not necessarily the performance of the antioxidant. So again, it won't correlate. And ultracentrifuge, which is a different variation of an NPC type test where it's measuring the level of contamination related to insolubles, it will not correlate. So all of these tests do not necessarily correlate with RPBOT. If they do, it's probably only under the most severe of occurrences. So just to help explain this a little bit further, let's go through those other tests that are listed. Now, we've already talked about viscosity and acid number, so we can move right on to NPC. Now, with NPC testing, what we're doing is we're taking a sample and we're running it through a 0.45 micron piece of filter paper. So we typically call these membrane patches or just a patch. Now, after we've run the fluid through the patch and we've dried it, we analyze it with a spectrophotometer. If you're saying, what's a spectrophotometer? Well, it's the same instrument we use in a hardware store to color match paint. It's an instrument that very accurately measures color. Now, if you understand measuring color, you might be familiar with the RGB scale that we use as an example in television broadcast and whatnot. You might be familiar with the CMYK scale that we use when we're printing, but we use yet a different scale here. It's called the LAB scale. And as you see in the picture there, the L value is basically a brightness darkness factor. The A scale is a green to red spectrum, and the B scale is a blue to yellow spectrum. What we concentrate primarily on is that L factor. How dark is the patch? Not necessarily what color, but how dark is the color that's on that patch. The darker the color, the more of the insolubles have been trapped on the patch. So to understand this, the limitation of this test is it only tells us how much of this insolubles, which eventually as they deposit, we would call them sludge, varnish, lacquer, tar. It only tells us how much is able to be trapped on the patch, which means it's how much is in the fluid. So it doesn't really tell us how much has already settled out within the system. So we have to appreciate that right away. It's kind of that constant joke I make with people about what any laboratory test can tell you is what's in the bottle. It doesn't necessarily tell you what's in your system, because if it's stuck in your system, well, you certainly didn't put it in the bottle when you sent it to the lab. So this test only tells us how much of the insolubles are in the oil. As for interferences, because we are measuring for darkness, anything else that will significantly skew the darkness of the sample may skew the results a little. So carbon is a good one for darkening oils, and carbon can come from electrostatic spark discharge, or it can come from microdieseling, and this may skew your MPC value a little bit. So knowing that MPC is a measurement of how much insoluble material is able to be trapped on that patch, understand that again, it won't correlate with the other tests that we've already mentioned. Just because you have insolubles in your oil doesn't mean you have a high enough concentration to affect the viscosity. Just because they're insoluble doesn't make them acidic, so it might not alter your acid number. RPVOT is a performance-based test, so it's measuring the performance of an antioxidant additive. It doesn't really care if there's any varnish precursors in the fluid. Ruler test is just a measurement of the antioxidant level, so again, it's not measuring the same thing at all. And ultracentrifuge, which is a measurement of varnish from a slightly different perspective, because of the method which it does it, not necessarily correlate well with MPC, which again is, like I said, why do we do two different tests? Because they offer us two different perspectives. So just to get on to that ultracentrifuge for a second, let's explain what this test is. It's a pretty simple test. You fill a test tube with oil and you spin it at a ridiculously high speed for 30 minutes. And the idea is that you're going to pull down everything of higher density than the fluid itself. Now, if it's a higher density than the fluid, the assumption is that most of it will be insoluble, so varnish precursors. And basically, when we conclude the test, we pull the test tube out and we look at the bottom of the test tube and we compare it to the visual scale you see there. And simply put, the top half of the scale is considered okay and the bottom half of the scale is considered bad. So we don't get too concerned about the actual value. We just accept that, generally speaking, 1 through 4 is not bad. 5 and higher, tends to indicate high levels of insolubles present in the oil. However, because we're pulling down anything that's of higher density, again, appreciate that this might not be just insolubles. It could be other particulate, but the same limitations apply. Just because we see it in the test tube, and even if we assume it's entirely insolubles, it's what's in the fluid, not necessarily what's in the system. Also, this test, because we're spinning it at such a high speed, we're potentially imparting energy into the sample, causing it to heat up. If it heats up, some of those varnish precursors will stay more soluble, and they may not settle out as easily. To compensate for this, you can obviously cool the sample a little bit, but if you over chill it, what you'll get is you might end up with more insolubles settling out than would necessarily normally do so, so the results might skew a little bit high. And like I said, anything of higher density is going to appear at the bottom of that test tube. So if it's something like water or particulate, well, that's going to contribute to what we see. So right away, hopefully you can appreciate that this is measuring varnish precursors, or insolubles as we call them, from a completely different perspective than MPC. So it should be appreciated that though one test might be high, the other test could potentially be lower or higher. You don't really expect a direct correlation. So saying that, the ultracentrifuge should not be expected to correlate with any of the tests we list. And I don't need to run through this again. We've already covered why that is. It's just a different perspective. Now, hitting the last test that we haven't talked about, the ruler. The ruler is a measurement of the antioxidant level. Now, how it does this is a rather multi-step procedure, but I can try and simplify it by saying this. Essentially, what we're going to do is we're going to take your sample and dilute it in an electrolyte solution. So if you're thinking Gatorade, you're not too far off. That is an electrolytic solution. What we then do is we apply a voltage to it, and we measure the voltage over time. And it's what we call a voltammogram, is the picture that's produced off to the right. Now, the concept is each antioxidant additive will produce its own unique signature, if you will, curve with a peak in it. So what we do is we measure the area of that peak. Now, as long as we have a sample of new oil, we know what that peak looks like at its best. And essentially, we measure every used sample and compare it back to the original new oil sample. So when we say there's 50% of the additive left, it's based on that new oil comparison. So we do need to have a sample of the new fluid. What this means is we can't do this test if we don't have the reference sample, and we also can't necessarily justify an entire decision about what to do with the oil based on a single result. Because even if you get a result comes back and it says, well, your additive level is at 30% of new oil value, your first question should be, well, how fast is it dropping, right? RULER is an acronym for Remaining Useful Life Evaluation Routine. So it doesn't just measure remaining life based on the percent of the additive that is present, but if you trend it, it measures how fast it's degrading. And if you extrapolate the trend, you can predict when that antioxidant is going to give up, and you should change your oil of course before that was to occur. Now, as for interferences, this test does rely on that new oil reference. So if you don't have it, well, we can't really perform the test. But if you've got a mixture, if there's more than one product in there, and sometimes this is because a product is no longer available, or sometimes because you switch suppliers, what we end up is with different peaks in different areas. So the picture I've included there is two completely different oils from actually the same supplier, but just showing how the additive chemistry is radically different. So without a proper baseline, we get some really messy results here, and they might look abnormally low, or sometimes, and this is what gets funny, they can look better than new. So it gets really confusing when we start seeing results like that. So ensure that you have a proper baseline sample submitted to the lab so that you can do this test correctly before you worry about trying to interpret the results. Now, since this test is actually a measure of how much antioxidant is present, it doesn't necessarily know how it's going to perform. So that's why it won't necessarily correlate with RPVOT, because that's a performance-based test, not an additive level test. And we've already talked about the other tests. Well, we're just not necessarily going to see a direct correlation. So to summarize everything that we've covered here and try and give you something applicable to take home, this is how I like to walk people through a report. When I tell people that report interpretation is ultimately left up to the end user, sometimes they're a little bit surprised. They always question, they go, well, isn't the lab supposed to do that? And, well, yes, the lab is supposed to offer their opinion, but you, the end user, might know a bit more about the circumstances around the lubrication of that component, around the maintenance activities. You know what impending turnarounds or shutdowns you might have. There's a lot more information in your head to properly interpret the report. So here are the steps as I see that you should go through to properly interpret the report and make sure you get the correlations where they exist and you avoid the ones when they don't exist. So as you see here, read the whole report, top to bottom. If you need to use a ruler and slide the ruler slowly down the page so that you don't skip ahead, whatever you need, but make sure you read the report from top to bottom, don't skip anything. As you read the report, you're going to see each line will contain a bunch of values of the same data. When you do that, ask yourself, do you like or do you not like the result? Doesn't matter if the lab has identified it as in alarm or not, you just decide, does that seem abnormally high or low? Now, when you do decide that it's abnormal, all I want you to do, and this is the key thing here, is simply categorize it as to a cause or an effect. Now, don't try and figure out what caused it. Don't try to figure out what its effect is. Just categorize it as an effect or a cause. So you're asking yourself, did this cause that or did that cause this? If it's an effect, we can move on. If it's a cause, we hold that one until we get to the end of the report. Now, by the time you get to the end of the report, you may have changed some of your answers. Some things you decided were causes, you may have said, no, actually, that's an effect. And there are effects of the effect, so that's not of concern. You want to summarize in hopefully only one or two causes by the time you get to the end of that report, and you're going to decide now what will truly investigate that cause. So my example here that I'm giving you is very infrequently is changing the oil solution. So many times people see bad data on a report and they schedule an oil change, and while to be fair, it will correct the data, it didn't actually fix the problem. It's just putting fresh oil in. So we need to say, what is the true cause and what would prevent it from recurring? We still might change the oil, but we need to take some extra action here. So just to finish off the presentation, let me walk you through an example. Now, I've taken a report and I've split it across 3 slides just to make sure it's readable for all. So reading the report from top to bottom, as you go down, like I said, every time we see something that we don't like, some trend that is abnormal or values that we don't think are correct, we simply ask ourselves, is it a cause or an effect? So as we go down this report, probably the first thing that you're not going to like is the iron value. And in the most current sample, it's even been alarmed by the lab. Now we ask ourselves, is iron a cause or an effect? Well, iron is wear typically. So we're going to say it's probably an effect. Something is causing the wear. This is just the effect from the wear. Copper, there was no copper. Once we get to lead, lead has taken a significant increase from the last sample. So again, don't like it, cause or effect? Well, did iron cause lead? Did lead cause iron? Does lead cause other things, or does something else cause the lead to be there? And again, you probably settle on something else causes the lead to be there. The lead is a wear metal, something else is causing the wear to occur. So far we have iron and lead as effects. We keep reading down the report. Now, no other wear metals were seen. Once we get to the additives, you might notice that the additives don't measure up quite closely with the new oil reference, but in history have trended quite closely. So again, I could look at that and say, well, I don't like the values because they don't measure or don't match the baseline. However, I might just decide, well, maybe the baseline is not entirely up to date. And I look at the overall trend and say, well, it's been steady. That seems normal. So again, I'm probably not going to pick anything out of the additive section and say that there's any significant problems. Once I get to silicon, however, now this has not been alarmed by the lab, but looking at the results, do they seem to have had a significant increase? Well, rather than simply looking at the jump from 7 to 14, look at the overall trend. It was 6, 9, 7, then 14. So I'm not necessarily going to say, well, it doubled in the last sample, because that's not really a fair assumption. It's hovered around 697, so it's been an average of 8, now it's 14. Seems like a significant jump. So would wear metals like iron and lead cause the silicon to be high, or could the high silicon cause the wear metals to be high? And hopefully you're deciding that the silicon is probably a cause. Again, the wear metals are an effect. So I actually now at this point have a cause. That's all I'm concerned about is the cause. I'm not deciding how it got there, why it's there, anything yet. I'm just assigning it a cause. So silicon is one cause. Moving on to the next section of the report, we look at the infrared spectroscopy, and we see very, very steady trends, so nothing significant there. But then we get to the particle count. Now, the particle count is a couple codes higher than it was in the last sample, and that even was higher than the previous sample, so there's been an overall trend upwards, but the last jump was a bit bigger of a jump than any of the previous jumps. So particle count probably going to stand out as something abnormal. Now ask yourself again, is it a cause or an effect? Well, did the wear metals cause the particle count to be high? Potentially. Did the silicon cause the particle count to be high? Potentially. So is this really a cause, or would we classify it as an effect? Well, it's kind of sitting on the fence, because now that we've learned what we've learned, we know that we're measuring particles that are even larger than what we would see in the iron, the lead, and the silicon. So this particle count may represent things that aren't seen on the rest of the report. So though you might lean towards saying that the particle count is a cause because it should be effects of that lead, iron, and silicon, I'm going to assign it definitely in the cause column. So I've got high silicon and I've got high particle count as causes. When we look at viscosity, we don't see anything really trending differently than in viscosity. It is different than the baseline value, but it's been steady throughout its history. Same thing goes with acid number. We see a fairly consistent increase in acid number, which is expected over time. Doesn't really match up with the baseline information. Once we get to water content, we see there has been a steady increase in water content, with the last two samples showing some much more significant jumps than previously. So we look at that and we say, well, is that an effect? Would high iron or high lead cause the water content? Well, no. Would high silicon cause the water content? Again, no. And would high particle count cause the high water content? No. So it's not an effect. It's got to be a cause. So at this moment, we have got water content, particle count, and silicon all as potentially causes. When we get to the last part of the report, and I didn't bother including the pictures, I was just looking at the data here, we've got our analytical ferrography. Now, when we look at the analytical ferrography, the first two rows, rubbing wear and rolling contact wear, are typically considered to be normal wear mechanisms. However, the size of particulate always plays a key role here. And what I'm seeing is some fairly large size particles contributing to the high or heavy amount of rubbing wear. So that's not normal. And I ask myself again, would this rubbing wear cause the iron and lead? Sure. Could it cause the silicon? No. Could it cause the particle count? Possibly. And could it cause the water content? No. So it's not necessarily causing all of the things we listed as effects, but it is causing some of the things we listed as causes. So we have to ask ourselves, what do we do with the other things we've listed as causes if we're going to add this to our list? So hold that thought for a second. Let's just read the rest of it. Once we get to sliding wear and rolling and sliding wear, those are considered abnormal wear modes. So an abnormal wear mode, never a good thing, and the size of particulate we're seeing here is very, very large. So this is definitely not good. So is this a cause or an effect? Well, what would cause sliding wear? Well, a lack of lubrication could do it. Now, could that lack of lubrication be because of the viscosity? Well, no, we confirmed the viscosity was correct. But what if the water content was high? What if water was displacing the lubricant? Well, then that might be an effect. If we keep reading down, we don't see anything else until we get to corrosion. Now, corrosion is not very high, but again, corrosion, is that an effect of water content? Sure, so it's an effect, we move on. Dark metallic oxides, though, that is a byproduct of what we call welding, and we don't mean welding as in like somebody was actually welding nearby or welded pipe together. It's welding as in two surfaces came under such high pressure the contact temporarily welded to each other, and as they pulled apart, metal was lost. So this comes into play with that sliding wear. So seeing sliding wear in dark metallo-oxides definitely indicates a lack of lubrication separating the parts. So these start to look like significant causes of maybe a bunch of the other stuff we're seeing. Then we hit red oxides, which is a fancy way of saying rust, which is another form of corrosion, but related strictly to iron. So does this explain the iron content, the water content? Sure, but it's an effect of that water content. So we won't add it to our list of causes, we'll keep it as an effect. And when we get to the last line, have any data on dust and dirt significantly high. So that helps support the silicon and the particle count. So those three seem to be related, dust, dirt versus silicon versus particle count. All those are related. So we have definitely got particulate in the sample, and based on the sliding wear and the dark metallic oxides, we do seem to have contacting metal parts as well. So put the two together and say, if we have contacting metal parts and we've got particulate getting in between them or abrading against them, we're probably going to experience that significant wear. But none of this addresses why the water is there. But does having the water explain it all? Well, having the water would explain why we have a lack of lubrication leading to sliding wear and dark metallo-oxides. If those were to occur, that would subsequently explain why the iron and the lead is present. And that would also explain why the particle count's going up. And this kind of cascading logic is what we use to interpret the reports, and we decide, what are we doing next? So though we had high silicon, particle count, and dust and dirt, we don't necessarily go inspect the breathers or change the oil based on that data. We realize there's another driver to this, and it could be viscosity related due to the water content, and it definitely is wear related based on the other data. So we could investigate what's causing the water to get in, which would be a good first point of action. But we also need to look at, why is there such significant wear? Well, the viscosity itself didn't suggest there was a lack of lubrication, but what if the load has changed? What if it's misaligned or imbalanced or just under heavier loads? That could explain a lot of other things. We might go investigate some operational parameters. But essentially, that's how you walk yourself through a report. Go from top to bottom, assign a category of cause or effect. Like I said, you can change your mind as you go through. Whatever logic gets you there, if there's any outside factors you know that could be affecting this, like you started running it more frequently or under higher loads, or it's hotter outside, or any other considerations, think of them and ask yourself, would they help promote what I'm seeing here? Is that my true root cause, and what can I do to investigate to confirm if that is in fact what's happening and not something else? So with that, I will turn it over to any questions we might have. I do thank you for taking the time to listen to our webinar, and apologize for the scheduling snafu there that suggested it happened at midnight last night. But if there aren't any questions that you're going to ask now, you have my email address on screen there. More than welcome to answer questions offline. So with that, I'll turn it back over to Taylor and see if there's any questions that have been submitted.
All right, thank you, Evan. All right, it looks like there's a few questions here. All right, Evan, which test will correlate with ruler?
Well, like I said at the beginning, why do we have different tests? Because they look at it from different perspectives. So we don't necessarily expect any test to correlate with ruler directly, because ruler is a measure of an antioxidant level, not the performance of it. So the closest test we have that actually would correlate directly would be infrared. There is some antioxidant additives that are measured through infrared technology, and those might correlate with the ruler. I say might because, again, they're measuring it from a different way, so the way we would get those results are a little bit different. Ruler does require a new oil reference, and it's always comparing back to that, whereas infrared does not require a new oil reference and is just a direct measurement. Now, the overall trend of those two results should be in the same direction, in that they would both decrease accordingly. But no, ruler won't correlate, as I said, with any of the other degradation or basic chemical property tests like acid number, viscosity, RPVOT, ultracentrifuge, or MPC. they might, but typically don't expect them to. Right? That's the point of this presentation, was to try and highlight some of those things that we normally expect that aren't actually true all the time. Right, what was the next question?
All right. And would water cause high or low viscosity?
That depends on the form the water is taking. When water content is dissolved, typically as it increases, it will cause a decrease in viscosity. Once water begins to form an emulsion, or is actually free water, which will clearly form an emulsion, then the viscosity will actually turn around and cause an increase. But at first, water typically causes a decrease in viscosity until such time as it's severe, and then it will, like I said, turn around and will cause an increase in viscosity. So a little bit of both, just depends on how severe the situation is.
All right, it looks like there's a few more, but they would be better answered through email. I'd like to thank everyone for joining us today, and thank you very much, Evan, for presenting.
All right, thank you, Taylor.